we started learning about the finite element method, and we just took a quick overview of what the finite element method does for us. So we said we're going to refer to it as FEM. And just before I move on, I would like to refresh here some of the vocabulary that we've learned. So the first one here is FEM. FEM stands for finite element method. As soon as I mention the finite element method, what comes to mind? There are elements, and it's a numerical method. We look at a continuous system that is difficult to solve in its own analytical. So we divide and conquer. So we divide it into elements. And we looked at different type of elements. These elements are connected together at nodes. So we choose the type of element. Adjacent elements connect at nodes. The elements and the nodes makes the mesh. In the finite element method that we're going to be using, we are going to keep it very simple. So we are going to focus on linear, elastic behavior. And this really requires a material that behaves linearly. So as in sigma equal to E times epsilon. So you see here the stress is directly proportional to the strain via a constant. It can also be expressed in relating the force to the displacement as we do in linear springs, right? So we can have here, I can write it as F equal to K times delta, where K is the spring constant. I think you all remember E, and E is constant also. So this is where we're getting this linear relationship. When we define elements, depending on the element types, we can identify degrees of freedom. So the degrees of freedom would be the displacements. And I'm going to keep S here, because these could be translational or rotational displacements at the nodes. And the total number of degrees of freedom are the displacements at the nodes that are required to provide the displaced state of the system or the structure. We also mentioned numerical solution and the use of matrices. So we can express the behavior of the system using linear algebraic equations. Using a system or using algebraic equations here. At the element level, we had element stiffness equations. We refer to as ESE. And we express them as lowercase f equal to lowercase k multiplied by d for displacement. Said there is also a global stiffness equations, GSE, for the entire system that I can express using an uppercase F column matrix multiplied by stiffness matrix K multiplied by D, the displacement column matrix. We also learned about, or I can write it here, the element stiffness matrix is this lowercase k, and the global stiffness matrix is the uppercase k. Both lowercase k and uppercase k are square, symmetric, singular matrix, meaning I cannot solve the equations as they are. So we also learned about boundary conditions. We need to apply the boundary conditions in order to solve the global stiffness equations for the unknown. I think this was most of the vocabulary we used. The lowercase f here is for element forces, and the uppercase f for external forces. Today, would like to dig a little bit deeper using a very simple element, the simplest possible element, a one-dimensional spring element. So today I'm going to move into spring and bar elements. And these are 1D elements. So they extend along the x-axis. Is the screen clear, or would you like me to zoom in? It's good. Okay. So it's 1D, so it extends along the x-axis. And usually the element would fill in a geometry. And it extends between at least two nodes. So here I have a node 1 and a node 2. And here is my spring element. This spring element It's a linear spring, so it has a spring constant K. And because everything is happening along the x-axis, at each node, I have 1 degree of freedom. 1 degree of freedom at each node. So at node 1, I have a U1, and corresponding to that displacement, I will also see an F1. At node 2, I have my 2nd degree of freedom, U2. And I have a corresponding element force, F2. And please note, I'm using a lowercase f. And this spring may have a length L. From what we have learned about springs, that they can be in tension or in compression. So let me put this spring in tension. What's going to happen to it? It's going to tend to elongate. And here this is under tension. So now when I put this very same spring under tension, I'm gonna get a delta and the relationship between the tension and the delta may be given by T equals to K times delta. How can I measure delta if I know U2 and U1? The elongation is going to have to be the difference between U2 and U1. So we can say that delta is equal to U2 minus U1. Therefore, T may be expressed as K times U2 minus U1. Now let me compare the top figure to the bottom figure. Based on the bottom figure, I can say that F1 is equal to minus T, which I can write as equal to minus K times U2 minus U1. Or I can write it as K times U1 minus K U2. And I'm going to call this equation 1. Now, F2 is equal to T, which is equal to K times U2 minus U1. I can write it as equal to minus K U1 plus K U2. And I'm going to call this equation 2. If I put these two equations in matrix form, I can write it as F1, F2 equal to U1, U2. And I put here a matrix. For F1, I have a K times U1, and I have a minus K times U2. For F2, I have a minus K times U1 and a plus K times U2. These are known as the element stiffness equations. I'm going to put it here. Where we can write that as F equal to K times D. Spring element stiffness matrix K is equal to a K minus K minus K and a K. Of course, we can also take the K as a common factor and put here a 1, a minus 1, a minus 1, and a 1. So we started here with a spring. If I move to a bar, you will notice that a bar has a cross-sectional area A and a modulus of elasticity E and a length L. And a bar is like a two-force member. So I can represent the bar or the relationship of the forces. This bar being a two-force member could be in tension or in compression. So if this is in tension like this, it is going to elongate delta. And as we have learned from solid mechanics, that this delta is equal to TL over EA. If I change the order of this, I can write it as T equals to EA over L times delta. Which if I compare this to the spring, T equals to K times delta, I can say then, therefore, K is equal to EA over L. So a bar element may be represented exactly like we did the spring, using two nodes, 1 and 2. And at each node, we have 1 degree of freedom. So I can have here a U1 and a force F1. I will have here a U2 and a force F2. And by the way, F1 and F2, we're going to refer to as element forces. And you can think of them as internal forces. So this is for the bar element, which looks identical to what we have seen for the spring. If that's the case, we can also show that the element stiffness equations may be written as similar to what we did for the spring. But now I can replace K with EA over L. So a bar element behaves like a spring that has a spring constant K equal to EA over L. So the element stiffness equations for a bar would be F1, F2 equal to, I can take EA over L as a common factor and go like 1 minus 1 minus 1 and 1 multiplied by U1 and U2. And we can say that the stiffness matrix K for a bar element is equal to EA over L times 1 minus 1 minus 1 and 1. F1 and F2 are element forces. You can think of them as internal forces. U1 and U2 are nodal displacements. Of course, at node 1 and node 2. So if we look at this element, what's the total number of degrees of freedom that the element has? 2, right? 1 degree of freedom per node. That's why I said we're going to keep it to the simplest. But remember, this bar element can only elongate along the x-axis. So it's a 1D element, and also we're getting the uniaxial deformation, only along one axis. Of course, in practice, a bar element may be used in plane, and it could be at an angle, could be like this. But just to keep things simple, we're going to continue to working with everything happening in one direction only. Now, of course, X could be horizontal. So in other words, the X-axis is aligned with the axis of the bar or spring element to make things simple. If we have an assemblage, usually that X-axis oriented along the axis of the bar or the spring is referred to as the local axis. And then we have another set of axes for the structure called the global axis. And we need to go between local and global using transformation. I don't want to do that here. We're going to just keep it simple and keep everything in the same. So if we're going to have an assemblage, it's also going to be along the same axis. So let's look at an assemblage of how we put more than one element together. So now this could be 2, could be 3, could be 4, could be any number. Again, just for the sake of keeping it simple, I'm going to start by putting 2 springs connected together. So I'm going to show here spring 1 extends between node 1 and node 2, has a spring constant K1, and this spring has a length L1, and I'm going to connect to it another spring, spring 2. So spring 2 is going to extend between node 2 and a node 3 and has a spring constant K2 and has a length L2. So now I'm looking at the assemblage. I'm looking at a system. Now this system could be subject to external forces applied at the nodes given by uppercase F1, uppercase F2, uppercase F3. So I would refer here to the Fi's are external or applied forces. Now everything is happening along the x-axis. So if I want to describe the display state of the spring, assemblage here, node 1 is only allowed to move along the x-axis. So I only need 1 degree of freedom to represent where it's going to go. So I'm going to give that by U1. Node 2 is also going to move along the x-axis, and we're going to show the displacement using U2. And likewise, node 3, we're going to express its displacement using U3. So this here describes my system. I have 2 elements, element 1 and element 2, and I have 3 nodes and 3 degrees of freedom. 1 degree of freedom per node. Next, I am going to separate the elements and look at each element separately. So I'm going to look here. At element 1, and here I'm going to be looking at element 2. So this has a K1, this has a K2. This is node 1, this is node 2, this is node 2, this is node 3. And since we just separate them, but because they form a structure, after the formation, node 2 has to keep the 2 elements connected. In order for node 2 to do that, that would mean both element 1 and element 2 are gonna share the displacement of node 2. If node 2 moves to the left, both elements at 2 are going to move to the left. Or to the right, they're going to do likewise. So this is called the continuity condition. In order for this system to remain intact or continuous, I'm going to get the same U2 on the connected elements. Now, node 1 for the element is still going to have a U1, and node 3 is going to have a U3. And please note, I'm using the same green color because these element displacements are going to be identical to the structure or to the assemblage or to the global displacements. Next, when we looked at elements, we looked at element forces. We looked at element forces. And I'm going to use another color for the element forces so that we can differentiate between element forces and external or applied forces. So at element 1, we have this F1 applied to element 1. At node 2, I have an F2 applied to element 1. And at node 2 for element 2, I'm going to get an F2 applied to element 2. Because these two could be different. At element 3, at node 3, I have F3 applied to element 2. Are we good so far? Next, I'm going to look at the equilibrium of each of the nodes. So I'm going to come here and I'm going to show node 2. Now, node 2 is acted upon by an external force, F2, and the elements are going to apply on node 2 an equal and opposite, right? So I'm going to get from this side an F2, and from this side an F2. Are we good so far? Now let's look at node 1 and at node 3. Okay. Now node 1 has an external force, F1, as well as the element is going to put F11. Likewise, node 3 has the external force applied to it, F3, and the internal, the equal and opposite of what's going into the element of F32. Next, I'm going to write the element stiffness equations. So element stiffness equations. I'm going to write them for element 1 and for element 2. So for element 1, I have here F11 is equal to K1 U1 minus K1 U2, and F21 is equal to minus K1 U1 plus K1 U2. For element 2, I'm going to get F22 equal to K2 U2 minus K2 U3. Are you all following where I'm getting these equations from? For element 2, these are identical to the one we just derived here. Equation 1 and equation 2. Right? But for element 2, because it extends between 2 and 3, I am replacing U1 by U2 and U2 by U3. So this is where I came up with this. I also have an F32 equal to minus K2 U2 plus K2 U3. So these are the element stiffness equations. for element 1 and for element 2. Next, we're going to look at equilibrium of the nodes. So if I look at node 1, I can conclude that in order for node 1 to remain in equilibrium, then F1 has to be equal to F11. And looking at node 2, I see here that this F2 must be equal to F21 plus F22. And for node 3, F3 must be equal to F32 for the node to remain in equilibrium. So these are equations of equilibrium. What I'm going to do is I'm going to substitute from the element stiffness equations into these equilibrium equations. So I'm going to say this then is equal to K1U1 minus K1U2. Correct? For F21, this is equal to minus K1U1 plus K1U2. But then I have F22, which goes like plus K2U2 minus K2U3. For F3, it's equal to F32, which is going to be like minus K2U2 plus K2U3. I can write these three equations in matrix form. And by the way, these equations that relates the red F's, the uppercase F's, to the displacement, or relates the behavior to the action, these are known as the global or the structure equations. These are the algebraic equations. So these equations are the global stiffness equations that in matrix form we can write them as F1, F2, F3 equals to, and we're going to have this global stiffness matrix multiplied by U1, U2, and U3. And I'm going to fill in here. For line 1, F1 is K1 times U1 and a minus K1 times U2. And I don't have anything multiplied by U3, so I'm going to put a 0. Second line, I have a minus K1 U1. I have a plus K1 times U2. I also have a K2 times U2. So I'm going to come here and put a plus K2 times U2. And then I also have a minus K2 times U3. And for the last line, I don't have anything multiplied by U1, so I'm going to put a 0. Then I have a minus K2 times U2. and a plus K2 times U3. Which we can write as uppercase F equals to this uppercase K multiplied by D, where K is global stiffness matrix. And I have a few comments here to mention. If we look carefully at this global stiffness matrix, it's a 3 by 3. It's a square matrix. The diagonal is always going to be positive elements. So the elements on the diagonal are always going to be positive, because it relates the behavior at a particular node to the displacement. The square matrix is symmetric, minus K1, minus K1, 0, 0, minus K2, minus K2. This matrix is singular. Cannot find an inverse. 4. If you also look carefully at this matrix, you will find that it is composed by superimposing the stiffness matrix of element 1 and the stiffness matrix of element 2, as represented here by the blue and the black. So if you look here, this is the stiffness matrix of element 1. And if you look here, this is the stiffness matrix of element 2. They are superimposed together, or we can think of it as the summation of the two element stiffness matrices, where each element is going to its proper location corresponding to the displacement and that it is relating to. So every time we are going to analyze a system, I do not necessarily have to do the equilibrium of nodes, but I can assemble this global stiffness matrix using superposition or using the direct method. So I will come here and say the direct method to assemble the global stiffness matrix. So this is the global stiffness matrix here. This is the uppercase K. So what are we going to do? In this method, I'm going to look at my structure. And first, I'm going to write the element stiffness matrices. So I'm going to come here and say, oh, element 1 has this stiffness matrix K1 that is equal to K1 minus K1 minus K1 and K1. And I'm going to have a K2, element 2, is going to have a K2 that is equal to a K2 minus K2 minus K2 and K2. Step number 2, we are going to label each row and column of the element stiffness matrices with its corresponding degree of freedom. So what would that mean? I'm going to come here to K1 and say, oh, element 1 extends between 1 and 2. So row 1 must be related to the first degree of freedom U1. And row 2 must correspond to the second degree of freedom U2. And column 1 would also relate to U1 and column 2 to U2. I'm going to go to element 2 and say, okay, element 2 extends between 2 and 3. The first row relates to U2, second to U3, likewise first column and second column. Next, we are going to expand the case to the size of K by adding zeros. Okay. So for example, for this problem, what is the size of K? The size of K is equal to the total number of degrees of freedom of the structure. So in this case, the structure here has 3 degrees of freedom. So basically, for the example, we can say that this K is going to be a 3 by 3 because total numbers of degrees of freedom is equal to 3. So what do I mean by expand this? I'm going to write K1. If you look at this K1 is a 2 by 2, right? And this K2 is a 2 by 2. I'm going to write it as a 3 by 3 here by going like K1 minus K1 minus K1 and K1. And I have a third row and a third column. And in these expansions, I'm just going to put zeros. And I can still keep my labels U1, U2, U3, U1, U2, and U3. And I'm going to do the same with K2, express it as a 3 by 3 equal to. This is going to be U1, U2, and U3. And the lines are still going to follow what I did for K1. So now if I want to fill in here, these are going to show as a K2 minus K2 minus K2 and a K2. And I'm going to fill in zeros everywhere else where I do not have entries. Is that step clear? Now, the direct method, step number 4, we're going to say that assemble K, where K is equal to the sum of all the K's from I equal 1 to N. This is Ki. So K is simply assembled by superimposing the expanded element stiffness matrices together. So let's apply it. So I'm going to come here and I would say that K, which now we know is a 3 by 3. So this is U1, U2, U3, U1, U2, U3. I'm going to put a K1 minus K1 minus K1 and a K1. And I'm going to add to this K2, each element going into its correct position. So I get here the plus K2, minus K2, minus K2, and K2. And of course, I still get a bunch of zeros, actually only 2 zeros now. So this is how we assemble this 3 by 3 K matrix using the direct method. And this is actually how the finite element method, when it utilizes computers, this is how we arrange everything such that we can program the computer to write the element stiffness matrices and use the direct method to assemble the global stiffness matrix. Once you have the element stiffness equations, in step number 5, you're going to have to apply the boundary conditions to solve the global stiffness equation. So the global stiffness equations are given by F equals to K times D. And what do you do here? You solve for unknown displacements and for the unknown forces, which could be sometimes the reactions. So once we have all the displacements known, we're going to move to step number 7 and use the element stiffness equations to solve for the element forces these F's, which we can think of as the internal forces. And we can use the F's here to find stresses. And we can use the D's to find the strains. So this is sigma, and here is epsilon. Okay. So this is how we are going to apply the finite element method or the direct method to solve a problem. Okay, I'll be happy to post them online. You don't have to worry about taking pictures.
Yeah, just uploaded it.
No worries. No worries. Now, when we come back a week from today, after we take the exam, and we have here the bases, we're going to apply what we just learned